I solved my problem. Yeah.
Okay, perfect. Okay, hi everyone. Welcome to the fourth edition of WeSST. Today we've got, in our fourth seminar, we've got Rosa Espinosa Marzal from the University of Illinois at Urbana-Champaign and Clelia Righi from the University of Bologna. So Rosa will talk first about molecular mechanisms underlying the lubrication of ionic liquids, and Clelia will talk about advancing solid interfaces and lubricants by first principles molecular design. Rosa, if you could load up your slides, please.
Yeah. It's okay?
Yeah, perfect. Yeah, so take it away, Rosa.
Okay. Thank you very much for the introduction, James, and thanks to Chiara and to James for the invitation to talk in the fourth session of WeSST. Today I am going to talk about molecular mechanisms underlying lubrication by ionic liquids, and let me start thanking the students and postdocs that have contributed to this work. Mengwei Han, he is a PhD student in my group. Pratima Nalam, she was a postdoc, now an assistant professor at the University of Buffalo. Alexis Shehan and Andres Jurado, who graduated already from my group. For those of you that are not that familiar with ionic liquids are low temperature molten organic salts. That means they are composed of anions and cations, like for example, cooking salt, sodium chloride. In the case of sodium chloride, we have very strong Coulombic interactions between the ions so that they are arranged in a crystalline structure. And these crystals are solid at room temperature, and we need to heat up to 800 degrees Celsius to melt the salt, and then it becomes a liquid. In the case of ionic liquids, I don't have a pointer. In the case of ionic liquids, at least one of the ions is polyatomic and of organic nature. This reduces the charge density and also increases the configurational entropy. And as a result, the ions are less well organized. They don't form a crystalline structure, and they remain liquid over a wide range of temperatures. And many of them are liquid at room temperature. Here you see some examples of cations and anions. This is the imidazoleum cation. I will focus on this cation in my talk. It can have different lengths on the alkyl chain. Here we have a TFSI anion. I will also focus on this anion in my talk, and another anion as example, the FAP. Chemists can synthesize many different of these ions, and that means that ionic liquids open up an unprecedented number of possibilities to modulate the intermolecular interactions in a low temperature, in a single room temperature solvent. The subtle equilibrium between the intermolecular interactions and the entropic effects yield several interesting properties to ionic liquids, like, for example, many of them have a supramolecular structure, but also they have a low vapor pressure, high thermal stability, high electrochemical stability, and a moderately large viscosity. And these are all properties that are important from the point of view of lubrication. This is the outline of my talk. I will start describing what we know about the structure of the boundary films. Then I will focus on the influence of water on lubrication from the perspective of an elastic viscous model. I will then move to the nanorheology of confined ionic liquid films to be able to answer one open question that we have in the friction model. And if I have time, I will talk about the effect of roughness on ionic liquid lubricity. To investigate the structure of the confined ionic liquid films, we use a surface forces apparatus, an SFA. For those of you that don't know much about SFA, in the SFA, the ionic liquid is confined between two mica surfaces. The mica becomes negatively charged in contact with the liquid, and the mica is coated on the backside by a silver thin film, and so light shines through it. It is reflected multiple times between the silver mirrors, and the transmitted interference is analyzed in our surface forces apparatus by fast spectral correlation. And this numerical algorithm provides a real-time measurement of the film thickness with sub-nanometer precision, and also a measurement of the refractive index with time. One of the surfaces is connected to a normal spring, and so it deflects. We measure the deflection, and therefore we measure the normal force. The other surface is connected to a lateral spring that deflects laterally, and so we measure the lateral deflection, and with it, the lateral force. So we can perform both normal force measurement, friction force measurements, and also nanorheological measurements. The information about the structure of the boundary film comes from normal force measurements. This is a representative measurement for MMTFSI for this ionic liquid. The force normalized by the radius of the mica, about 2 centimeters, and as a function of the surface separation, which is the thickness of the boundary film. You see that the force is positive. This means there is a repulsion, and so to squeeze out the liquid, we have to apply a force. At large separations, this force scales exponentially with the separation, and there are results and works that have demonstrated this is a force of electrostatic origin, but I will not talk about this today. I will focus on the shorter range force that indicates, or is what we call a solvation or a structural force, and as you can see, there are some steps embedded in the force profile. These steps reflect that the ions are organized in layers, and every time we squeeze out one of these layers, we measure a step. And from the thickness of these steps, we can determine the thickness of the layers of ions. And here you have briefly some representative results for 3 different ionic liquids, the 3 of them with the same anion. And in the cation, we vary the length of this alkyl chain. We have an amine, so an ethyl group, a bemine with the butyl group, and H-mine with the xyl group. And you see that for the amine and the bemine, the thickness of this layer is about 7.5 angstroms, and 7.5 angstroms is about the size of an ion pair. So we conclude that we have layers composed of anions and cations. We don't know how they are organized. This is a cartoon where I just plotted them alternating anions and cations, but we really don't know how they are organized. But they have the same number of anions and cations to maintain electroneutrality. And then here you have the results for the H-mine, so an xyl group here, and the thickness is about 1.2 nanometers or 12 angstroms, which is larger than the thickness of or the size of an ion pair. And following the work by Susan Perkin, we also presume that what we have here is cation bilayers, so the cations self-assemble due to solvophobic interactions, and then we have anions intercalated again to preserve some electroneutrality, and this explains why these layers are much larger than for amine and bemine. Now, what happens when we equilibrate the ionic liquids with humid air? Here on the left, you have representative results for the force versus the surface separation or film thickness for this ionic liquid, MMTFSI at 0% relative humidity. We measure the red data points, and then at 15% and at 30% relative humidity, you can clearly see that the curves shift to thinner films. So for each force, we have a smaller film thickness. The thickness of the layers does not change massively. We see about 7 angstroms, also in the presence or in equilibrium with humid air. And only for the smallest films of about 2.5 nanometers, we observe a small expansion of about 1 angstrom. This expansion is really very ionic liquid specific. So for other hydrophobic ionic liquids, we measure perhaps an expansion of 3 angstroms, and this essentially depends on the chemical composition. So what happens now with the friction force? These measurements were carried out by colloidal probe AFM. This is a silica colloid sliding along a mica surface. The diagram shows the friction force as a function of the normal load for the same ionic liquid, either equilibrated with dry air or with humid air. And you can see that the coefficient of friction increases by a factor of 2, by about 2. These results are at 1 micron per second, but this trend, I mean that the friction force is higher for the wet ionic liquid, remains the same or qualitatively the same over a wide range of velocities. You see here results between 0.5 microns per second to almost 300 microns per second. The different symbols represent different loads between 15 and 75 nanonewtons. This diagram here at 0% relative humidity, and here at 44% relative humidity, with much higher friction forces. Now, let me zoom in here to see how the friction force changes with the sliding velocity. You see here a small decrease of the friction force with an increase of velocity, very subtle, and then a prominent increase of the friction force with velocity. At 44% relative humidity, the friction force remains quasi-independent of velocity at the slow velocities that we measure, and it increases again almost logarithmically with the sliding velocity. If we calculate very roughly according to Hamrock-Dawson model, the thickness of the films here, considering some results that I am not going to present about the viscosity of the ionic liquids under confinement and the prominent increase that we measure, we obtain thicknesses that are about 8 nanometers, for example, at 10 microns per second. And this tells us that the thickness here is much larger than here. So we have a kind of hydrodynamic lift. And we assume that above this transition velocity, we move into the hydrodynamic lubrication. And below this transition velocity, we are in the boundary film lubrication. So a very thin film of ions separate the two surfaces and provides a good lubrication. So we have tried to describe these results from a quantitative point of view, very simple, with an analytical model to try to understand what water is doing here. And so we have used the elastic viscous friction model. So it considers that there are two contributions to the friction force: an elastic component that is more prominent at the slowest velocities, and a viscous component that is most prominent at the highest velocities. Given that we observe a logarithmic increase of the friction force with velocity, we use a model for hydrodynamic lubrication based on Eyring's law for viscosity of liquids that exhibit shear thinning. And I will talk about shear thinning later again. This equation describes such model, and it depends on the shear rate, the velocity divided by the thickness of the films. It depends on an Eyring shear stress that is inversely proportional to the so-called shear activation length. And this cartoon represents more or less what happens in Eyring's transition theory. According to this theory, for a slip to happen, an energy barrier needs to be overcome. And the applied shear on the molecule decreases this energy barrier, and by a magnitude that is proportional to the shear activation length. And as you can see in this cartoon, This value is a displacement from the minimum of the energy to the maximum of the energy. Okay, and then it also depends on this viscosity parameter, which depends on the confinement. And again, I will talk later about this. Okay, the second component is the elastic component, and we use a model proposed by Drummond et al. For friction between surfactant monolayers, and that is based on Chalamak's model for rubber friction. And so it assumes that during sliding, multiple physical interactions between the ions at the slip plane here form and break. The bonds in this model by Drummond are called junctions, and the model assumes that these junctions are elastic springs, and the dissipation originates from the elastic energy stored during the deformation of the junctions and dissipated during the rupture of these junctions. The junctions are interactions between the ions, hydrogen bond, electrostatic interactions, and there are no covalent bonds forming here, but I will call it bonds anyway. According to this model, the friction force depends on different characteristic times. The characteristic time for the formation of the junctions, which I call here tau f, a characteristic time for the rupture of these bonds that is also based on Iron's theory. And the model also considers that the bond rupture can happen upon a stretching of the bonds. And so depending on which characteristic time is relevant, friction can decrease with the speed, increase with the speed, or be speed independent. We have simplified this model by considering that the rupture of these junctions is only thermally activated. This gives us an analytical expression for the elastic component of the friction force that we can fit to our results. You can see it depends also on a phi parameter, which gives the probability that this bond forms, and it depends on the lifetime of the bonds and the time, a characteristic time for formation. So without going more in detail into this equation, let me show you what we learned when we fit this model to the experimental results. The line showed that the fit is okay. And I will only show you the parameters that tell us something about the role of water on the lubrication by these confined ionic liquid films. This diagram shows the characteristic time, tau, in milliseconds for the bond rupture and for the bond formation as a function of this parameter that I didn't describe, which is the junction length. It's essentially the film thickness. And what you can see is that when we add water, the film thickness decreases, which is consistent with our normal force measurements. So that's good. And second, we see that the characteristic time for the bond formation decreases by about 1 order of magnitude, which means that water favors the interactions between the ions at the slip plane. And both factors together explain or justify the increase in friction in the elastic contribution. For the viscous term, we cannot determine the viscosity. It cannot be unambiguously determined because we don't know the thickness of the films in the hydrodynamic regime, but we can determine the shear activation length. And you can see that the presence of water molecules significantly reduces this shear activation length, and so more with an increase in load. And that means, according to Eyring's model that the mobility of these molecules under the applied shear stresses decreases in the presence of water. Furthermore, because we have assumed a model that presumes shear thinning behavior for the ionic liquid, from the good fit from this model to our results, we conclude that there is a shear thinning behavior. But to really make sure that this assumption is correct, we perform nanorheological measurements with the SFA. The measurements consist of confining the ionic liquid, moving the upper surface in an oscillatory motion, and measuring the lateral deflection. And here in this cartoon, you see in black the applied displacement, The blue data points are the deflection, and you see that it is also oscillatory. And from here, we determine the amplitude of the deflection as well as the phase difference. And knowing these two parameters, we can determine the complex viscosity, if we have a viscoelastic behavior, an effective viscosity, which is variable, it's not a complex number. Here you have the equations for the two components, and we can also determine the storage modulus and the loss modulus. So when we determine the storage modulus and the loss modulus for the ionic liquid here at 0% relative humidity confined to different thicknesses as a function of the frequency, what we observe is that when we increase or when we decrease the film thickness, there is a prominent increase of the storage modulus. For the bulk ionic liquid, we have a viscous liquid, so G prime is 0. But when we confine the ionic liquid, for example, to 1.8 nanometers in red, we see the storage modulus and the bulk modulus become of the same order of magnitude. That means that confinement leads to a transition from a viscous behavior to a viscoelastic behavior. So we have films that have both elastic and viscous properties. So we also obtain the effective viscosity, and those are the only results. I want really to go into a little bit more detail here. Here you see the effective viscosity of the confined ionic liquid films at 0% relative humidity as a function of the shear rate. And the prominent decrease of the effective viscosity with an increase of the shear rate indicates that we have shear thinning behavior, which is good because that's what we had assumed. So prominent shear thinning behavior. Second, we learn the following. Imagine we start with a film thickness of 10 nanometers. This is a force measurement, so somewhere here. And now we squeeze out one layer and get a thickness of around 9 nanometers. In these diagrams, these are the pink results. And you can see that there is a jump of the effective viscosity by more than 1 order of magnitude. Now we compress the ionic liquid to 5.7 nanometers. We don't squeeze any layer, and you see a small increase of the effective viscosity. Now we squeeze out a layer, the number 4 here, and have a film thickness of 2.9 nanometers. And again, we have a prominent jump of the effective viscosity, and then we compress it to 1.8 nanometers. We don't squeeze out any further layer, and the increase of the effective viscosity is minor. This tells us that the effective viscosity is quantized. It means that the effective viscosity is mainly dictated by the number of confined layers and not by the compression. The same measurements were performed at 30% relative humidity, and this diagram is very confusing, so I will try to navigate you also through this diagram. The empty symbols are for the humid ionic liquid, and we have here results at 9.4 nanometers. We have here results at 5.7 nanometers, as well as here 2.2 nanometers in red. It's very difficult to measure, to do the rheological measurements at the same film thicknesses as the at dry conditions, because we have a shift of the force curve, and also there is a relaxation when we approach the surfaces, and so we never achieve exactly the same film thickness. But if we compare the results at 2.2 nanometers at 37% relative humidity with the 2.9 nanometers at 0% relative humidity, you see that water reduces the effective viscosity a little bit. And so that's an effect that we also see from the rheological measurements. So I have 2 slides about roughness. I'm not sure if I have enough time. I need like 4 minutes. Should I go ahead?
Yes, go ahead.
Yeah, okay. So this is a very different story. It's about the influence of nanoscale roughness on the lubricity by ionic liquids. And here we prepare substrates, silica substrates, with different roughnesses by sintering silica nanoparticles. You can see here an example. By changing the number of silica nanoparticles, we increase the RMS roughness from 0.7 nanometers to 6 nanometers. These measurements were performed with this ionic liquid, so a longer alkyl chain here in the cation in the same anion. The measurements were conducted by AFM with a silicon tip at high pressures, higher than 60 megapascals, up to 1 gigapascal, and you can see how the coefficient of friction increases with roughness, with the number of nanoparticles. And this is intuitive. We have higher pressures at the nanoscale asperities. We squeeze out more ions, and so the remaining ions are less efficient in lubricated, and so the friction increases. But interestingly, when we perform measurements with a silicon oxide sphere at pressures that never go above the 60 megapascals, we observe a minimum of friction at the intermediate roughness for the substrates with 275 nanoparticles per square micron. This indicates that we have some competing mechanisms. This can happen, but in addition, perhaps, and based on MD simulations, it's possible that the disorder films on the rough substrate, which we confirm in normal force measurements, are responsible for a decrease of friction. And this disorder essentially favor less the interactions between the ions at the slip plane. But to consolidate a little bit more these results, we perform independent measurements by colloidal probe AFM, and these are hydrodynamic force measurements. So here we approach a sphere rapidly against the rough substrates in the ionic liquid. We model the hydrodynamic force by Reynolds' theory of lubrication and introduce a potential slip on the surface with Vinogradova's model, which uses a slip function that depends on the slip length. You see that a larger slip length implies a larger slip velocity and also a smaller hydrodynamic force. And this is the last diagram I want to show you. This is the slip length as a function of the approach velocity for the three substrates. The smooth one here, about 40 nanometers, the highest roughness has the smallest slip length, which is intuitive again because the roughness hinders the flow of the ions, so it brings the ions to a still state, and the slip length is close to zero. But again, at the intermediate roughness, we have the largest slip length. We don't know why. It can be that the structure of the ions is different close to the surface, because that's what we measure in the normal force measurements. It can be that it's about the disorder. We don't know exactly, but the point is that this FASTA, or ease of slip of the ions on the surface, correlates with our minimum coefficient of friction in the friction force measurements. And so we see there this correlation, and this would imply that we could tune friction also by modifying the nanoscale roughness when lubricated by ionic liquids. That's all. I have a slide with conclusions very briefly. I started with talking about the boundary films and the layer structure. I show how trace amounts of water, small amounts of water, can have an important effect on the structure of the films. It makes them thinner, it changes relaxation times, and it decreases the effective viscosity. We also saw in nanorheology a transition from viscous to viscoelastic behavior and a prominent shear thinning behavior of the confined ionic liquids. And I show you some new results on the effect of roughness on ionic liquid lubricity. With that, I want to thank funding, my group, collaborators, and of course, all of you for your attention.
Thank you very much, Rosa. That was a really nice talk. So I'll start with a question from James. Have you measured the contact angle of the ionic liquids on the rough surfaces? maybe similar to slip of water on super hydrophobic?
The truth is not on these surfaces, but we have done a lot of work on the correlation between contact angle and a slip length of different ionic liquids, and we don't see any correlation. And we have a potential explanation why, but the truth is we haven't done it in these surfaces. So, however, I wouldn't be surprised if there is no correlation based on our other measurements.
Okay, maybe I have a quick question myself. So there's, you haven't done any tests with temperature. Do you know how stable this film would be with temperature?
Are you talking about the roughness or?
Sorry, the ionic liquids.
We have performed, only SFA measurements, not AFM measurements with ionic liquids. So, which is in fact the interesting part, because we are talking about thermal activation. So it would be interesting to see it there. But we haven't done it yet. What we plan to do is the nanorheology temperature dependence. And that's something we have in mind.
Great. With that, I thank you very much.
Okay.
And now over to James.
Thank you very much, Rosa. So our next speaker is Clelia Righi from the University of Bologna. Can you share your screen, please, Clelia?
If Rosa
I think,
is,
Rosa, if you could stop sharing first. There we go.
Okay, thanks, Rosa. Okay, let me share my screen. Okay. 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 Can you see my presentation?
Yeah, perfect. Thanks. Yeah, take it away, Clelia.
Okay. Thank you, James and Chiara, for your effort in organizing this nice event. And thank you for who is listening. I have entitled my talk as the ERC project that I'm going to start at the University of Bologna, the aim of which is to advance solid interfaces and lubricants by first principle material design. So friction and wear result in massive economic and environmental costs. And decreasing friction, even by a small amount in every car engine, can result in a huge reduction of fuel consumption and carbon dioxide emissions. So we have the effective opportunity to contribute to these global challenges by advancing the technologies to reduce friction. And these technologies are nowadays based on materials. However, in comparison to other technology based on materials, tribology is less advanced because of the complexity of the phenomena occurring at the buried interface during sliding, which are difficult to monitor in real time by experiment. So simulation can play a very important role in this context, in particular those based on quantum mechanics, which is essential to accurately describe the electronic clouds in conditions of enhanced reactivity as those imposed by the mechanical stress applied. And the adhesion at this nano-size contact affect the macro-scale friction coefficient. And the functionality of most lubricant material is precisely to reduce this adhesion, either by covering the surfaces with inert layers or coatings, or by tribofilms that are formed in situ through stress-assisted reactions involving lubricant additive. Our knowledge on tribochemical reactions is still limited at present, and we developed computational tools to perform a study of tribochemistry. They include ab initio molecular dynamic programs that we have modified in collaboration with Professor Ferrario and Carlo Cavazzoni to simulate sliding interfaces. And we have linked to larger scale models such as in a QMMM approach, linked to classical MD in a QMMM approach, and to green function molecular dynamics in collaboration with Seiji Kajita from Toyota Center Lab to perform a multi-scale description of the tribological interface, including the elastic response of the semi-infinite bulk. We have applied these computational tools not only for fundamental understanding, but also for practical applications. For example, in collaboration with Toyota Center Lab, we have studied how to improve coatings that are used to cover parts of the engine. Measurements available in their lab show that silicon dopants can reduce the friction coefficient of DLC diamond-like carbon for reasons that were not fully understood. So we performed ab initio molecular dynamics simulations of sliding diamond surface interfaces interacting with water molecules as those present in humid air. And we found that the presence of silicon atoms, here represented in blue, favor the surface hydroxylation. You see that silicon atoms capture these hydroxyl groups and enhance the reaction rate for molecular dissociation. And this is consistent with the energy barrier that we calculated from static first principle calculation that show that the presence of silicon atom can reduce the barrier for water splitting to half of its value. And the chemisorbed hydroxyl group participate in the hydrogen bond networks of surrounding water molecules, so that a layer of water remain bound to the sliding surface during sliding, and protecting the surface from direct contact and making it slippery. Another material whose lubricating properties are deeply affected by humidity is graphite. As you can see from the dramatic change of the friction coefficient of steel or steel lubricated by graphite in dry and humid environments. And different hypotheses have been proposed to explain this phenomenon. And one that we believe that is relevant is related to the presence of reactive defects, such as graphene edge, that can be created during the rubbing process that can degrade the lubricity of graphite, and passivating species are necessary to quench down the reactivity of this defect. To verify this hypothesis, we performed quantum mechanics, molecular mechanics simulations, considering a system of about 1,400 atoms, where the chemically active region, consisting here in graphene ribbons interacting with water molecules, was described accurately through quantum mechanics, while the rest of the system, where chemical reactions do not take place, is described by classical molecular dynamics. In this way, we could consider a large enough system to capture collective mechanisms, but still feasible from the computational point of view. You can see here the atom trajectories during the simulation from a lateral view and a top view here on the left of the quantum region. First of all, you can notice that the water molecules escape from the intercalated region. And this rules out a proposed hypothesis on the effect of humidity on the lubricating properties of graphite. We also observed many cooperative mechanisms of water molecules that are enhanced by their confinement that lead to an efficient passivation of the reactive edges. And the hydroxylated edges becomes hydrophilic and interact with other water molecules in the surrounding and also with other hydroxylated edge. Another research activity in my group concerned the study of the computational design of lubricant additives. In collaboration with Total, we study in particular extreme pressure additives that are compounds that in boundary lubrication conditions, when the thickness of the liquid oil becomes so thin that direct metal-metal contact can take place, these compounds interact with the metallic surfaces and modify their chemical composition with consequent modification of the adhesion and resistance to sliding. So it's highly desirable understanding how these tribofilm are formed and to design new environmental friendly, hopefully lubricant additives. So we started our activity in this field by studying the tribochemistry of organophosphorus additive. And in collaboration with the group of Jean-Michel Martin and Maria Isabelle de Barreau-Boucher at the École Centrale de Lyon, we studied the organophosphorus additive. They had this a measurement performed by gas-based phase lubrication experiments that showed that an effective reduction of the steel-on-steel friction coefficient could be achieved by including 3-methylphosphite the chamber. And the in situ spectroscopy analysis revealed that a tribofilm composed just of iron and phosphorus reduced friction. This problem from the computational point of view, we performed an analysis based on different stages. First of all, we identified the reaction path and energy barriers for molecular dissociation on the surface, on the iron surface. Then we evaluated how the reaction kinetics is modified by the tribological conditions. And we found that the reaction rate is highly enhanced by molecular confinement and the mechanical stress is applied. Elemental phosphorus was released at the iron interface as observed in the experiment. And we calculated the adhesion and resistance to sliding of iron interfaces and found that they can be dramatically decreased by the presence of intercalated phosphorus atoms and sulfur atoms. Sulfur is another key element for lubricant additives. Finally, we studied the electronic properties of these interfaces and found that the lubricating capability of solid sites in the electronic properties of these elements that interact with iron in a different way than other elements like oxygen, nitrogen, carbon that we have considered for comparison. We are studying another important friction modifier additive that is molybdenum diethylcarbamate. That is a compound, a class of compounds that are widely used in tribological applications due to friction coefficient very efficiently till to an order of magnitude as represented in this picture. It is well known since many years that this capability is related to the tribologically induced transformation of MODTC in molybdenum disulfide. And this process that occurs in boundary lubrication conditions is not fully understood. Different hypotheses have been made based on experimental observations. Back in 1998, it was proposed a mechanism that started with the molecular dissociation with the cut of the molybdenum-sulfur bonds. But 20 years later, another mechanism was proposed, and the dissociation, the initial dissociation, seemed to occur by breaking the sulfur-carbon bonds. The dissociation mechanism is not the only source of complexity, because it is known that the molecule oxidizes quite rapidly, and the role of oxygen atoms in the dissociation process is not clear. So we studied for the first time these processes by means of ab initio calculations. First, we consider the molecular dissociation and the dissociation of an isolated molecule. And we found that the weakest bond is that between the carbon and the sulfur atoms. The molybdenum and sulfur atoms. So this is the less energetically costly way of breaking the molecule, breaking the isolated molecule. Then we considered different isomers of the molecule and found that the most favorable position for the oxygen atoms is the ligand position. We also considered molecular oxidation and found that it is energetically favorable. And again, the most favorable location of the oxygen atoms is in ligand position. Then we consider the situation of molecules confined at iron interface in tribological conditions. And we perform the QMMM simulations and compare standard MeO-DTC compounds with oxygen-rich compounds. Here you can see the results of the simulation from a lateral view and a top view, where the two different compounds are compared. So for standard MeO-DTC, the dissociation at the iron interface occurs through the detachment of the carbamate units, while for the oxygen-rich MeO-DTC, the oxygen atoms remain attached to the carbon atoms. And here is even more clear from these snapshots acquired during the simulation, where the iron atoms are made transparent. But if you look at the pictures on the right, you can immediately see that in the case of oxygen-rich compounds, central units of the molecule containing just sulfur and molybdenum atoms are released, while oxygen atoms remain attached to the carbamate groups. So this could be regarded as a favorable situation for forming molybdenum disulfide layer by the connection of this central unit. And our study also solved the debated issue of the initial dissociation of the molecule, because we saw that it depends on different conditions. If sulfur atoms are present in ligand position, the bonds that are broken are those between the molybdenum atom and the sulfur atoms, while the situation changes if the molecule is in contact with the substrate. Instead, for oxygen-rich compounds, the bonds that are broken are always between molybdenum and oxygen atoms, and the oxygen atoms remain attached to the carbon atom of the carbamate groups. Okay, now I start the second part of my talk, which is on advancing material interfaces. As stated in the white paper of the Materials Genome Initiative, a key strategy for reducing the time and cost for materials discovery and deployment is to integrate the experiments with computational tools and digital data. And in this context, first principle high throughput calculations based on solving the fundamental equation of quantum mechanics for a large number of materials in a relatively short time have proven to be powerful tools for advancing materials-based technologies, ranging from batteries to catalysts. Surprisingly, they have not yet been applied to advanced interfaces for tribological applications. So this is one of the goals of the project. And we developed a protocol to calculate intrinsic interfacial properties from first principles. First, we calculated the work of adhesion, that is the energy required to separate two surfaces from contact. And then by monitoring how this adhesion changes as a function of the relative lateral position of the two surfaces, we can construct the stacking fault energy surface or the potential energy surface of the sliding interface. And from the corrugation and shape of this potential energy surface, we can derive the frictional forces that appear during sliding, and we consider the most negative one as the highest resistance force as to calculate the shear strength, the ideal shear strength of the interface for sliding along a specific direction. We applied this protocol to calculate the interfacial intrinsic properties of homogeneous interfaces. So the same materials is mated, and so here you can see the adhesion. We consider different surfaces for the same material. Here is the reported the adhesion energy for the lowest energy surface, and here on the right the corresponding shear strength. These parameters that are obtained from first principle can be used as input parameters for larger scale models, and their analysis allows to obtain, to derive general trends. For example, we observe that there's a power law between the shear strength and the adhesion of an interface, of a solid interface. We also studied the electronic properties of these homogeneous interfaces. When two surfaces are mated to form an interface, there is a charge redistribution. And it's possible to calculate this charge redistribution exactly in the same way as the adhesion is calculated. We also define a figure of merit to quantify this charge redistribution when an interface is formed. And we found that the adhesion between two surfaces is linearly related to the amount of charge that is accumulated in the interface when the two surfaces are mated. And this is also true for a large number of materials, including layer material, metallic, and covalent materials. Not only, we also found that the amount of interfacial charge that is present between the surfaces is maximum when the surfaces occupy a stable position, a minimum of the potential energy surface, while this amount of charge decreases when the two surfaces are displayed towards less stable stacking configurations. So during sliding, there is a charge redistribution, and the amount of charge that is redistributed is directly related to the corrugation of the potential energy force surface, and so to the frictional forces that appear during sliding. So we believe that this is an interesting result because it's a first connection between the electronic properties of the interface and the tribological properties. So in conclusion, I hope that I convinced you that ab initio molecular dynamics, eventually linked to larger scale methods, is a powerful tool to understand and that's improve the functionality of materials to reduce friction. I presented some examples concerning coatings, solid lubricants, and lubricant additives. And I've also shown that first principle high throughput calculation can be used to screen the tribological properties of hundreds of materials pairs. Up to now, we consider homogeneous interface, but we want to consider also heterogeneous interfaces. And overall, these computational methods allow not only to acquire understanding useful for practical application, but also to develop fundamental understanding. For example, we found a relation between the electronic properties and electronic properties, the electronic properties and the tribological properties of solid interfaces. So I like to conclude with a big thank to the people who actually obtained the results that I have presented. From the left, Giulio Fatti, Gabriele Losi, Paolo Restuccia, Michael Wallock, and Stefan Peters. I would like also to thank Professor Mauro Ferrario for his constant collaboration with our group, and our industrial collaborators, Sophie Lollet and Seiji Kajita. And I would like also to thank you for your attention.
Thank you very much for this fascinating talk. We have a question from Jorge from Capital Engineering, and he would like to know if you have any insight in the difference between graphite and graphene in their interaction with water.
Okay. Some experiments show that graphene seems less affected by humidity than graphite, which could be seen as a strange result because, of course, graphite is composed by many graphene layers. A possible answer that I can suggest is that graphene, we study graphene, for example, on iron, attached to the iron surface can absorb on it, and its reactive edge anchor to the surface. So they become, let's say, their reactivity is quenched down because these graphene flakes or ribbons are attached to the substrate. While in graphite, we have much more ribbons, edge, and so on, and they are also free. While graphene, being just a layer, can be more interacting with the substrate, and less defects can be present. So this could partially explain the observation that graphene seems less affected than graphite by humidity.
Okay, thank you. And I have one last question by James. For the molybdenum DTC, do you have thermal first principle MD simulations for the friction modifiers without compression or shear? And so what would be the effect of just the temperature for the dissociation?
No, we have considered, I don't know if I understood correctly the question, but in our QMMM simulations, we have temperature of 300 Kelvin, we have a load of 4 gigapascal, and a shear. So yes, these are, sorry?
Without the load of the shear, do you just know what would be the effect of changing temperature?
No. We haven't split the different factors. No, that could be interesting, yeah.
Okay. And this may be time for a last one. Ilya Ponomarev asked for the graphite water simulation. Did you simulate what happens to graphite ribbons in the same setup but without water?
Yeah. In this case, we perform just probably, I don't know if I have the simulation, but I can describe them. In that case, we perform just classical simulation based on the ribon potential, and we consider 2 diamond surfaces lubricated by graphene flakes. And in one case, graphene flakes were passivated with hydrogens, and the other case were not. So in the case when no passivating species are present, these flakes form the chemical bonds with the 2 surfaces and the system was stuck. Even if there was a lateral force, sliding couldn't take place because these very reactive flakes locked the interface. While for hydrogenated flakes, they become parallel to the surfaces and sliding could take place. These results are published in the same paper, in the same carbon paper where we presented the QMMM simulation. So it's possible to see, because we also asked ourselves what happens if we remove the passivating species, and the effect is dramatic for sliding.
Thank you very much. I think that's all the questions we have time for, and over to James for the conclusion.
Okay, yeah, just like to thank our speakers again. Thank you very much, Clelia and Rosa, for great talks. So next week we have Victoria Van Camp from SKF and Ashley Martini from the University of California, Merced. It'd be great if you could tune in again. We also have our posters up now. We had our poster competition on last Thursday. All of the entries are still on the website at westtribo.com. And yeah, you can still see all of them there as well as on Twitter, so please have a look. We had some great entries, and we're hoping to have our winners present over the next few sessions to show you their posters. Yeah, so just thanks everyone, and see you again next time.